Hello guys, welcome to this definitely work. In this part, that is part number 3, we will be having a look at the embedded code that will implement the algorithm that we have discussed in part 2. If you have not watched part 2 and part 1, I will strongly encourage you to have a look at those parts. I mentioned their links in the description section. And so let's get started with the code. Alright, so now let's go through the code that we are using in this project. Yeah, you have gone through the schematic, so then also let's go. I'll just talk a little bit on that. We are using LM35 as our temperature sensor. Then we'll connect switches to the port B for deciding the logging time, and temperature sensor is connected to any channel of the. I mean, you can connect it to any channel. Here we are using ADC1. There is no constraint on channel number. Then we are using this UART for communicating our data to the PC, where we'll plot using we'll plot the log data by using the Python script. Excuse me. Here we have included this basic AVR files. You can say the IO, delay, interrupt, and boolean header files. Next, we have this few variables. The logging time. This will decide the delay between two logs. Then this USART data count was just for debugging purpose. Then this boolean variable enable data will decide whether to enable the delay or disable the delay. Then these two, the low ADC and the high ADC variables, will store the value of the digital converted data. Then these two functions, yeah, will go through as we will proceed. Then now let's go through our main code. We are enabling our port B as input port because we have connected the switches to the we have connected our switch to this port to connect to decide the delay. And we are enabling the internal pull up because our switch, when they are in open case, port B will read high, and then depending on which switch is pulled down, our delay will be decided. Next we are putting, I mean, this LEDs were just for debugging purpose. You can skip if you want. Now let's configure the ADC. In this we are using we are not changing anything to, I mean, we are keeping prescaler to default, that is clock frequency by 2. Then we are making our ADC reference as internal 2.56 volts, and ADC channel 1 is decided. So that we can see here, this 001 will decide our ADC1 channel, and this 11 will select our 2.56 volt internal ADC reference. Then next we are enabling the ADC interrupt and enabling the ADC. Now we are next to enable our global interrupts. Then we will initialize the UART. So let's go to this function now. Where is our initializing UART? Yeah, here it is. So in the UART initialization, here we are setting the baud rate. This baud rate is set to 4800 bits per second. Because I'm using internal 1 megahertz clock oscillator, so this will give us, I mean, above this rate we'll get error of more than 3%, which is not acceptable. Next we are enabling our TX and RX, then setting the frame format to 8 bits and 1 stop bit, and then we are enabling the interrupt. So as soon as I do that, we'll get this data register empty interrupt, USART data register empty interrupt, and it will go into this USART data register empty vector, and it will send some. This is send our ADC low and ADC high, which are already set to 0 in our when we declared them. We have set them 0. So it will just send those as 0 and then disable itself, and this port D LED will just toggle its state to indicate that it has entered into this ISR, interrupt service routine. So after it gets disabled, the next statement will be issued, that is our ADC start conversion. And so as soon as our ADC completes its conversion, it will get into its ISR, that is ADC vector ISR, and here it will enable the delay. This enables the delay for, this will put the delay between this conversion and when to take the next conversion. So, and here we'll put our data into these two variables, ADCL and ADCH will be copied to this register. Then yeah, we are just keeping our user data count to 0 because we are not sending anything. And then yeah, as our interrupt was disabled, this will enable the interrupt, and again it will toggle the state of another LED which will indicate that we have entered into this ISR. Yeah, you can disable, comment this part because this was just for debugging purpose. So after this ISR, after it gets out of this ISR, it will reach into this our while one loop, that is continuous, that will be executed every time. So it will just take the reading for our logging time, and it is not of port B because we have pulled high the register. We have pulled high this port, so when it will read everything as one, we don't need the logging time equal to 256, but that will be equal to 0. So this loop won't be executed, and this is just for having correlation between our switches and the logging time. Otherwise that it will be like kind of a not relation that is difficult to understand. So this is better to have a not here. So this won't give any delay. Again, the enable delay will become false, and we'll start the next conversion. So in case if you are having every pin open, every switch open, then this will be like continuously convert the data and send it to the UART. But if you have pulled down any of the switches, then according to its binary value, we'll get the delay loop. The number of times this delay loop will be executed, and we'll get the delay correspondingly. So yeah, so after this data gets converted, again we are starting the conversion. So let's go through this loop once more. Again, if we start this conversion, it will go to, as soon as the conversion is finished, it will go to its ISR, again take the data, then enable the UART interrupt. So if you enable the UART interrupt, it will get into this UART interrupt service routine, and it will, I initially told that this UART data count was for debugging purpose, but sorry for that, it's not for debugging purpose. It just, because we are here using the 10-bit conversion mode, we need to send 2 bytes. The lower byte will be sent when this UART data count is 0, and higher byte will be sent when this UART data count will be equal to 1. So first we'll send the lower byte, and then we'll send the upper byte. So this thing will continue in a loop, and we'll get the data as you, depending on the whatever delay you have set. So yeah, this is the code that we have used. If you have any doubt regarding the code, you can mention that in the comment section. Thank you. So if this video looks nice to you, please like this video, and if you don't want to miss any stuff that definitely works, you can subscribe to this channel. Thank you.